applications of calculus to the physical world, but in particular the rate of change that is motion. That's what we're really interested in here. So some terms. Displacement, we talked a bit about that last time. Now we tend to use x a lot for the pronumeral in motion. It doesn't have to be x, of course. It could be any pronumeral you like. But I guess there's obvious ones you wouldn't pick. Like you wouldn't pick t. Well, you're going to confuse yourself because time obviously is involved here. I think in physics we use s a lot, don't we, for displacement. So x is what we tend to go with. But when you're talking about two-dimensional motion, so you've got both the x direction, but then we might introduce y for the y direction. And of course, if you have a three-dimensional problem in the real world, you might introduce a z direction as well. Okay. So it's basically distance, but with direction. So it's telling, are you going this way or are you going that way? So then velocity as opposed to speed. We now have a couple of different ways we could write velocity. V, I guess, is the obvious one for velocity, but it is a rate of change, so you could say dx to t. Then you have the dot notation. Now the dot notation in calculus is actually Newton's notation. We tend to reserve the dot notation specifically for motion, because motion was what Newton was all about. So we really only use it in these motion problems. So it's the rate of change of displacement with respect to time. So speed, but again with direction now. So the negative sign tells you you're going in the opposite direction. And then the next important one is acceleration, which obviously A for acceleration. You could now write it as dv dt, rate of change of velocity with respect to time, or perhaps you say the second derivative of displacement with respect to time. And using the dot notation then, it would be x with two dots, because it's the second derivative, or v with one dot. So they're all different notations we could write down for acceleration. And that's the rate of change of velocity with respect to time. Okay, now there's this thing called deceleration, which you need to get out of your head, because there is no such thing as deceleration. Okay? Deceleration, or slowing down, the way we think of it is not that. Okay. We are still accelerating, but in the opposite direction to which we're travelling. And so that creates you slowing down. So that's what people think of as deceleration. But it's not actually deceleration. You're still accelerating, but in the opposite direction to which you're travelling. So here's a travel graph, displacement time graph. Not linear, because now, because it's displacement, not distance versus time, we could have negative numbers on our axis as well. The slope at any particular point would be the instantaneous velocity. We talked about that the other day. And that's what we're more interested in, is these instantaneous things. Now, we could then draw a velocity graph. Essentially, it's the derivative graph of my displacement graph. It would end up looking like this. And how do I tell? Well, I know things like at turning points, the derivative is 0, so they must become t-intercepts in this case because it's a t-axis. I know inflection points will become a turning point, so we've got that. And also looking at it, kind of looks like a cubic. It makes sense you end up with a quadratic when you differentiate. Now, a slope at any point here then would be the instantaneous acceleration, because you differentiate velocity, you get acceleration. And then you could keep going. You could draw your acceleration time graph. And for this one, well, if I differentiate a quadratic, it would be a straight line. So we'd end up with something like that. So, all right, back to those traditional questions. What's the distance travelled? Well, 7 metres. I go back to my displacement time graph, but I'm talking about distance, not displacement. So I've gone up 2, down another 2, up 1, 7 all up. Total displacement, so how far away am I from my original position? -1. I'm 1 metre away, but in the negative direction. What's the average speed? Okay, well it'll be 7/4, distance over time. Whereas average velocity, displacement over time, -1/4. But we don't need the graph, and that's what we were saying before. That's the beauty of it now. If we've got an equation for the curve, I can use my calculus to do the work for me. So we know if we were to draw it, it would be this curve, x equals t cubed minus 21t squared. So it's travelling. Now, because that's a curve doesn't mean the particle is travelling in a curve. The particle is still travelling in a straight line. It's just governed by this function, which happens to be a curve. To find the acceleration, well, essentially it's just saying find the second derivative. All right, so xt cubed minus 21t squared, velocity then becomes 3t squared minus 42t, acceleration 6t minus 42. With those three equations, I should now be able to solve any problem they give me. Find the times when the particle is stationary. Remember, you're presenting your solutions for someone else. So you explain why you're doing things. So I'll make a statement. Well, hang on, I know the particle is going to be stationary when v equals 0, which I guess is similar to the statement we'd be making curve sketching. We'd say, oh, well, stationary points occur when the derivative equals 0. Same sort of thing. All right, we'll go and solve that quadratic with two values, but again, answer the question. You can get fancy, and instead of saying t equals 0, you can say initially. So the particle is stationary initially, but then again after 14 seconds. Alright, so we've got this one. A particle, again, moving on the x-axis, which is very convenient. It tends to move along this x-axis a lot. It starts at rest from t equals 0, and at the point p equals 7. Doesn't always start at the origin. Doesn't have to start at the origin. If its acceleration at any time is 2 plus 6t, find the position of the particle when t equals 3, so after 3 seconds. So this time I'm starting with acceleration. So now I'm going back the other way. I'm going to have to integrate to get the velocity. This is where the constant becomes very important. Because if you don't have your constant, you're not going to get the right answer. So we're looking for some initial conditions in there that I can substitute in, and it said it starts from rest. So in this case, when t equals 0, v equals 0, if I had forgotten my constant, I would have got away with it, because it actually turns out to be 0 for this one. But now we go and find displacement, and we're not going to be as lucky, because we didn't start at the origin. So subbing into that one, oh, x is 7 initially. So there's my equation. T squared plus t cubed plus 7. We want to find when t equals 3. So now we just, a substitution question, sub it in. We get 43, so okay, I know after 3 seconds the particle is 43 units and it's to the right of the origin. You could say in the positive direction, you could say x equals 43. I mean, there's different ways of writing that down. But as I say, the constant, forgetting it is a common mistake. And here's how I avoid forgetting it. And how I avoid forgetting it is never finding it in the first place. What? Instead of writing acceleration as a, I write it as dv to t. And what I'm now going to do is this technique called separation of variables, which we will see when we look at differential equations. But essentially I'm looking at this and saying this is an equation. So if I multiply both sides by dt, but then integrate both sides. And this is why when we did integration by substitution, we said do not mix your variables. Never mix your variables. Because you should, in something like this, end up with a statement that you could solve easily. So on the left-hand side, I had the integral of dv. On the right-hand side, I have the integral of 2 plus 6t. The dt and the dv now becomes important. So some of you often forget your dx's and things like that when you're doing integrals. These now become very important. Now, the limits, because this is a definite integral. They told me when t equals 0, the velocity was equal 0. So I matched the limits up. At the top, that's what I'm trying to find. So I just put the pronumeral there. I want to know what v is at t. Now I just solve the problem. Well, the integral of dv is just v. When you're going from 0 to v onto v, going straight to v is not an issue. Because integrate, well, 1, you're going to get v, sub in v, you get v, minus sub in 0, oh, you get v. That's okay to jump straight there. The other side, not so much. We can't just assume that. So I end up with 2t plus 3t squared, but yes, when I sub in 0, I do get 0. But there's velocity. Now I go and do the same thing for displacement. Instead of writing down v, I write down dx to t, separate the variables. Match up the limits. We were told when t equals 0, x is 7. I want to know what x is when t equals 3. And now it becomes a very simple thing to solve. Left-hand side, now it's not going to just be x, so I do put the limits in, okay, going from 7 to x. So on the left-hand side, I get x minus 7. On the right-hand side, I've got 3 squared plus 3 cubed. Move the 7 over, I've got 43. So I have no problems about forgetting my constant because substituting in those numbers are working out the constant for me at the same time. So personally, I think it's a far more efficient way of doing it rather than going and finding the constant and doing all that. Okay, let's look at some HSC ones. 2001. Here's an interesting one. X equals t minus 2 on t plus 2. T is measured in seconds, displacement in metres. They're the normal sort of ones. Simple question to start off with. What is the displacement when t equals 0? Bit of a gift marked. Oh, thank you very much. Sub in t equals 0? -1. Answer the question though. I've wrote it as 1 metre to the left of the origin. Again, you could say in the negative direction. You could say, oh well, it's at x equals -1, or show that. This is where they're really giving them a huge hint. Show that x equals 1 minus 4 on t plus 2. Well, the easiest way then is to actually work from the answer and show I get that t minus 2. Algebraic fraction, and oh yeah, look at that. I get t minus 2 on t plus 2. They are indeed the same thing. Velocity, I'm going to differentiate because it does say hence find the expressions for. Minus the derivative on the function squared, but in this case it's also multiplied by the 4, or the -4. Acceleration, again I can go minus the derivative on the function squared, and there we go, there's acceleration. Is the particle ever at rest? Give reasons for your answer. I'm still questioning whether my reason's acceptable. I simply went, oh well that's velocity, well that can't equal 0. There you go, that's my reason. Can't equal 0. Therefore it's never at rest. Yeah, possibly I should have said something like, well, when you've got a constant on the top of the fraction or something like that. But what is the limiting velocity of the particle as t increases indefinitely? So in other words, what's the limit of velocity as t approaches infinity? Well, we found an expression for v. What have we got? We've got this hyperbolic function. If I think of the graph, what's that doing? It's curving. So as we approach infinity, that's going to 0. That's our limiting velocity. Of course, you might actually draw the graph. I don't draw the whole graph, I'm only interested in t being positive, but the graph would look something like that, and we can see from the picture, oh yes, it's going towards 0. Okay, there's the limiting velocity. It's never going to actually stop, but it'll get slower and slower and slower. Let's look at the next year's one. A particle moves in a straight line, time t seconds, x meters. Oh, a trig function this time. Trig function. Sketch the graph. I suppose this is just a clever way of getting them to draw a trig graph, but making it look practical. So we've got to draw x equals sine 2t plus 3. So the sort of thing, well, amplitude is 1. We've shifted the whole thing up 3. The period is pi. I'm going to mark my divisions off there for every pi on 4. Draw my axes up, but again, I don't need the negatives. Really, we're only talking about positive time here. Because we've shifted the whole thing up 3, I know I'm not going to go down into negative displacement either. I'll just draw in x equals 3, so I've got that axis I know the sine curve winds along. It's a sine curve. Sine would normally start at the origin. We've shifted it up 3, so I'm starting there. I then go up, down, and there's my thing. Draw it in. Okay, we've drawn our curve. Using your graph or otherwise. Translation, use your graph. Don't go and use calculus for this question. You've now got a graph. When is the particle at rest? i.e., where are all these stationary points? That's all it's really saying. Again, you could waste a lot of time and differentiate and solve that equation. You've got a picture right there. Okay, well, it was at rest when velocity equals 0. We know that. When's velocity equals 0? Well, that's when the derivative is equal to 0. In other words, the stationary points. So yes, at t equals pi and 4. And that was at x equals 4, at 3 pi and 4, and so on and so on. I can just list them because I've got the graph. Describe the motion completely. Ah, this is the fun question. You can get carried away with these. What did I say? Oh, I used a big word, oscillate. The particle oscillates between x equals 2 and x equals 4 with a period of pi seconds. I think that pretty much describes it completely. Alright, so 9b, we'll do some motion questions there.